Hello and welcome to another video in this series as we journey from the very simple primes to the foothills of the Riemann hypothesis, one of the most interesting and challenging and still open problems in mathematics. Today we're going to be looking at a very useful technique which is used quite a lot in number theory. We actually did make use of it in the last video, but we didn't explain it. We said that the Riemann Zeta function converges for s is more than 1, but we didn't explain how, so we're going to do that today. I should say the technique is really simple but very powerful, and it's worth becoming familiar with because it's used, it keeps popping up, it's used quite a lot. So let's jump right in. So the core idea is that understanding the behavior of discrete functions is not as easy as understanding the behavior of continuous functions. So we've seen discrete functions which are, say, sums of integers or sums of functions of integers, like this harmonic series, for example. Understanding how it behaves, how it grows, how it changes takes a little bit more work and sometimes a lot of work, whereas understanding how a integral of a smooth continuous function is a lot easier, and that difference is the basis of this technique. So let's dive in with a question which is trying to explore the growth of the harmonic series 1 over n. What we've shown on this graph here is a continuous function 1 over x, and on top of it we've plotted the discrete function. We've plotted 1 over 1, 1 over 2, 1 over 3, 1 over 4, and we're going to compare the sums of those discrete areas, the rectangles, with the area under the curve, the smooth function. You might have spotted that actually there are green and pink triangles. The difference is simply that one goes above the curve, it's always above, and the other one is always below, and we can choose how we index our functions. We can say this is a function of 1, this is a function of 2, this is a function of 3, so that's 1 over 1, 1 over 2, 1 over 3. And if we're interested in the smaller area, which is always less than the curve, we can index it, so this is starting at 2, so 1 over 2, 1 over 3, 1 over 4. When you visualize it like this, you can see the core concept, which is that these green taller rectangles, the area of them is always more than the integral, the area under the curve. And the pink rectangles, the area of those is always less than. That's the key takeaway from this visualization. So if we look at a specific area, like say between 1 and 4, we've already seen that the area of the taller green rectangles, 1 plus a half plus a third, is greater than the area under the curve. We've just said that. We've said the area of these green rectangles, 1 plus a half plus a third, is greater than the area under the curve between 1 and 4. And we can write that down. And in fact, we can say that it doesn't have to go up to 4, it can go up to 10. We can look at a range from 1 to 50 or 1 to 100. In fact, we can say 1 to n, and we can make a general observation that the harmonic series summed from 1 to n is always more than the area under the curve, which goes from 1 to n plus 1. Let's look at that picture again to understand why it's n plus 1. It's easier to see with a smaller range. So if we were doing 1 to 3, 1 over 1, 1 over 2, 1 over 3, these three rectangles, the area under the curve is from 1 to 4. That's why it's n plus 1. So from 1 to n plus 1, because we're looking to the right of each rectangle, each x that starts the rectangle. And that integral is really easy to perform. Let's actually do that on a bit of paper. So I'm going to write out this integral here. So we've got 1 over x, that goes up to n plus 1, starting at 1, and that was the area under the curve, from 1 to n plus 1, dx. And we know that when we integrate 1 over x, it becomes a log, so it's log of x from 1 to n plus 1, and that's ln n plus 1 minus ln the logarithm of 1, which is 0. So that's the answer. That's the area under the curve. Very simple, just school mathematics there. And when we do that, we can say that the harmonic series summed from 1 to n is always more than the log of n plus 1. And that was a very easy, quick result, and it gives us a lower bound on the growth of the harmonic series, and that can be useful. And that wouldn't have been so easy to arrive at just by staring at the discrete series, 1 over 1, 1 over 2, 1 over 3. By comparing it in this way to a continuous function, we can extract something that's, yes, it's an inequality. We'd love it if it was not an inequality, if it's just an equality. But these are actually quite useful insights and quite powerful as well. Let's see what happens when we look at the other rectangles that are always less than the area under the curve. So if we look at that range again, say 1 to 4, the area of the shorter pink rectangles, which is now not 1 plus a half, but half plus a third plus a quarter, and that's less than the area under the curve. Let's go back to that picture to see why it's a half, a third and a quarter. So the pink rectangle is a half plus a third plus a quarter. So using that same idea again of saying, yes, we're looking at a range 1 to 4, it could have been 1 to 40 or 1 to 400. In fact, let's generalize that and say it's 1 to n. And here we're starting at 1 over 2. And we're saying that the harmonic series summed from 2 to n is less than the integral, the area under the curve, from 1 to n. Now, just in case we've got a little confused about why it's n and not n plus 1, and why it's 2 and not 1, let's look at that picture again. Let's consider the first 3 rectangles, which go from 1 to 4. So the area under the curve, the integral, goes from 1 to 4, 1 to n. We're not looking to the right now. In terms of counting the discrete rectangles, we are starting from not 1 but 2, because the first one is a half, then a third, then a quarter. So for the discrete sum, it's 2 to 4, and for the integral, it's from 1 to 4. So 2 to n and 1 to n. Great, and this is now less than the integral, whereas before we were looking at more than the integral. And we can fix that sum that starts at 2, because we can just adjust it by saying 1 plus, like 1 over 1 plus that sum starting at 2 is the same as the sum from 1 to n. So we can just substitute that into our expression. Really simple again. And if we perform the integral, I won't do it this time because it's the same. 1 over x becomes log x, and the limits this time are from 1 to n, and really quickly the answer pops out as the sum of the harmonic series from 1 to n is less than the log of n. It's plus 1 here because it was minus 1 on the other side. Now what this does, it gives you a upper bound. It means the harmonic series never goes above this expression. And that was really easy. That did not take a lot of work at all. All we did was we compared the harmonic series, the discrete function, with a related continuous function, and we made a general observation about which series are always greater than or less than the area under the curve. And because the area under the curve is a continuous function, it's much easier to manipulate. so that two really nice inequalities pop out, a lower and an upper bound. And actually, let's just test that. Here's a visualization. It's experimental. It's not proof, but we didn't use this visualization to prove the lower and upper bounds. We actually derived them. We're just looking at them to see what they look like. And you can see the middle curve is the growth of the harmonic series, and the top one, the upper bound, is log n plus 1, and the lower bound is log n plus 1. So that kind of, you can see how it works. So that's really nice. So the core idea there, the key principles are starting from the idea that continuous functions are easier to work with and understand how they behave than discrete functions. We therefore find a related continuous function for any discrete function that we're interested in. It's not always possible, it's not always easy, but often it is. And then we can use observations like the fact that the discrete sum is always more than or less than the integral. That can lead us to some really interesting insights. We'll do it again, and this time we'll ask a different question. This time we're not asking about lower and upper limits. We're not asking about the growth of the harmonic series. We're going to ask about our Riemann Zeta function. So we want to know for which s the thing converges. We have an intuition, and we talked about it in the previous video. We know through other means that when s is 2, the Basel problem, the thing converges to pi squared over 6, and that's what made Euler famous. We also know that the simple harmonic series, when s is 1, diverges. That's a very ancient proof that we talked about. We also know that when s is more than 2, it also converges because each of the terms is smaller. So the interesting question is, what about when s is between 1 and 2, less than 2? Let's explore that and use this same technique. So we've plotted this curve of 1 over x to the power s, and we've again plotted rectangles which are always above or below the curve. So we're starting in the same way. Now you might say, well, hang on, if s is less than 0, this curve is the wrong shape, it should be growing. And you're right, but we can rule out that possibility of s being 0 or less than 0. So the Riemann Zeta function is a sum n equals 1 over n to the s. And we're just thinking at the moment for s is 0 and s is less than 1. When s is 0, this thing is 1 over 1 plus 1 over 1 plus 1 over 1, which we know diverges. That's easy. For less than 1, we've got 1 over n to the minus something. It's a negative power, which means the thing is more than 1. Same with the next term. Each term, when s is less than 0, the fraction inverts, and then we have a term which is more than 1, and the same here, 1 over n to the, and so on. Right, now let's go through our same process of thinking about the areas of the rectangles compared to the area under the curve. So looking at a small area just to get started between 1 and 4, the area of the 3 shorter rectangles, the pink ones, is less than the area under the curve. We've said that before. We can generalize and say from 2 to k of the discrete function x to the s, 1 over x to the s, is less than the area under the curve 1 to k of 1 over x to the s. And again, we can perform the integral just like we did before, and we can also make this little correction for the fact that the sum starts at 2. We're doing the same little correction there, and performing the integral is just like before. Because it's 1 over x, and we know that s is, we can't say it's always log x. because s could be something other than 1. And you can easily perform that integral. In fact, it's worth doing it just once just to see. So the integral from 1 to k of 1 over x to the s dx. And this is the kind of stuff we've done at school, but we'll just do it slowly just once. This is 1 to k of x to the minus s. And remember, to do the integral, we raise the power by 1 and then divide by the new power. Do you remember when x becomes x squared over 2? It's the same idea here. That becomes x, adding 1 to that, 1 minus s over 1 minus s from 1 to k. And we can write that in several ways. We can just keep it like that, that's fine. Or we could put x underneath and write x to the s minus 1, but this is fine. So that was really, really easy. The integral is as simple as that. So evaluating at those limits, we get k to the 1 minus s over 1 minus s minus 1 to the 1 minus s over 1 minus s. And actually we can bring that fraction together. So 1 to the power of anything is 1, so that just becomes minus 1 there. Easy peasy. So that's what we've got here. Now let's look at that more closely. So the first thing we can see is that s can't be 1, and we already know this. It's the harmonic series which diverges. But more interestingly, if we look at the top of the fraction, as k gets larger and larger towards infinity, remember the upper end of that range that we were looking at, the area under the curve from 1 to k. Now if k goes to infinity, then the only way this is not going to diverge, because it looks like it will, k gets bigger and bigger, is if the power 1 minus s is less than 0. That's the only way this thing gets smaller and smaller. So 1 minus s is less than 0 gives us what we want. S is more than 1. Now if the integral converges when s is more than 1, because the integral is larger than the sum also converges for s is more than 1. Now when we're kind of beginning maths and learning this stuff for the first time, it's easy to stop there and say, right, we've got our answer, s is more than 1, and that's understandable. But actually, if you think a little bit more about it, there's a possibility that we haven't ruled out. So let me draw a picture to explain what that possibility is. So let me just draw two shapes here representing the sum and the integral. And we've said that the integral is always more than that sum. And we know that this converges for s more than 1. So for s more than 1, this converges as well. Converge, converge. But this is less than the integral. There's a kind of a difference. So it is possible, we have to rule out the possibility, that the sum could converge for a wider range. So maybe, s is more than, say, 0.9 or something else like that. Because let's just say that was the range for the sum. It's still true that it converges for s more than 1, but we need to rule out the possibility for s is 1 or less. Can you see what's happening there? It's too easy to stop at the point and say, right, s is more than 1, we've confirmed it. What we've actually confirmed is that the integral converges for s more than 1. The sum, being always less than the integral, will also converge for s more than 1, because it is always less than that. But actually there might be other s's for which it also converges, so we need to rule that out. Luckily, the answer is easy. So this time we're going to be looking at the taller rectangles, which are always more than the area under the curve. And again, we can start by looking at a small range just to get a feel for what we're doing, to get the limits right, and then we make the general observation from 1 to k that the area of the rectangles is always more than the area under the curve, which goes from 1 to k plus 1. And again, the integral is really easy to do, just like before. I won't do it because it's the very same idea, very simple, kind of nothing more than what we did in school. And we end up with this expression. It's very similar to the one we had before, but there's a k plus 1 this time. And again, we can make observations to say, well, s can't be 1, but the more interesting insights come from the top of this fraction. This time, we're going to say that this thing, yes, in order for this to not get bigger and bigger, as k gets bigger and bigger, 1 minus s needs to be less than 0, therefore s is more than 1. We can do that again, but we can actually look at this a slightly different way. We can say this thing diverges, not converges, diverges when s is less than or equal to 1. When s is less than or equal to 1, this power is always more than 0, which means this grows as k goes to infinity. So we're talking about divergence now. So if this thing diverges, the integral diverges when s is less than or equal to 1, because the sum is always larger than the integral, it also diverges when s is less than or equal to 1. And that's crucial to understand that. That's only possible to say because the sum is always more than the integral. And if the integral is diverging, so is the sum because it's more than. Now we've achieved what we wanted because we can now say the sum diverges when s is less than or equal to 1. And that's what we need to rule out that possibility that we looked at before. So before we said the sum converges when s is more than 1, we now can also say that the sum diverges when s is less than or equal to 1. Now we've completed the picture. And we can present our findings now. And they're so important, everyone knows them by heart. They just, it's part of everyday conversation for mathematicians. The Riemann Zeta function only converges for s is more than 1. So that was an illustration of that technique of comparing discrete functions with continuous functions, and in particular sums with integrals, in order to gain insights into how those sums behave. And that's how we arrive at this very famous result. In fact, we can combine those inequalities, and we have again lower and upper bounds for the Riemann Zeta function, which is useful because later we'll be exploring the behavior of the Riemann Zeta function a little bit more, or a lot more, and it's useful to know that it's always between these two very simple expressions. Fantastic. I hope you enjoyed that, and you can see that it's not too difficult at all. Very simple technique, but very powerful, and used a lot in number theory. See you next time. Bye.